Hello all, welcome to the explanation for problem 7.4 in the homework. Here's the problem statement for problem 7.4. The experimental data for the temperature versus B data is here, and you want to identify the boil temperature, at which the temperature B equals 0, the inversion temperature, in which the temperature of the partial temperature respect to the partial pressure, with H being constant, is equal to 0 for methane. It gives us a hint to plot B versus inverse T and get a trend line and differentiate analytically. Then it wants us to plot this plot versus the curve from 7.7 and use the points without experimental data and the lines without points for theoretical curve. So using the data in the problem statement, I just plotted the inverse of T versus the Boyle's number given in the book, and I got this curve. I used a second order polynomial, and I got an R squared of 0.999, which is very good. And I got the corresponding equation displayed there on the graph. You have to remember that x in Excel is 1 over t because that's how we plotted it. Use the solver in your calculator, and the calculator gave out that 514 is the temperature that the Boyle's number is 0. Here I have the derivation spelled out. The first row on the left is just the product rule, and then if you move the right 2 over to the right hand side, you'll end up with partial t divided by partial p at constant h is equal to negative partial h partial p divided by partial h partial t at constant p, which is the heat capacity. So we're just going to need to find the partial h partial p at constant t. We're going to be using the fundamental equation of thermodynamics. If we take that with respect to partial p, keeping t constant, you end up with T ds dp with constant t, which is a Maxwell relationship, and plus V dp dp, and that will just equal 1. So when you apply the Maxwell relationship, you end up with partial h partial p constant t equals to negative t partial v partial t constant p plus v. If we substitute that back into the first equation that we got with the product rule, you end up with T partial V divided by partial T constant P minus V divided by the heat capacity. We know that PV equals RT plus BP. If you just solve for V, you end up with RT over P plus B. And since we're looking for partial T, partial V divided by partial T with constant P, you just take the derivative of that and you end up with R over P plus partial B partial T divided by P. Now if you look over to the right side, we're going to substitute that equation that we just got over back into the partial T divided by partial P at constant H. Equation we just got and set it equal to 0. We know B from Excel, the line curve that was just given on the last slide, and we can take the derivative of that line curve. You can see B and the derivative of B with respect to T with constant P. There, you substitute those both in, and you're going to solve that using your solver on your calculator, and you end up with a final T of 975.331, which is corresponding to the temperature where partial T with respect to partial P at constant H equals 0. Part B of the problem statement told us to plot the data of inverse T generated from equation 7.7 and compare that to the plot that we used for inverse T of the original problem statement. The temperature, I used the exact same temperatures that were given in the original problem statement. It was mentioned that this is methane, so we can find the critical temperature, the critical pressure, and the rho. From the critical temperature, you can get the reduced temperature. And using the reduced temperature, that will give us B0 and B1. And you can find the boil temperature. All you need is the reduced pressure. Using the reduced pressure, I used the guess and check method to estimate if it's around 220. That would give us around the same boil temperature as the original problem statement, so it would be easier to compare. I then just plotted the boil temperatures with the inverse temperature, and that is using equation 7.7 on the right there. You give an R squared of 0.994, which is not as good as the original one, which was in problem 7.4, which we got the R squared of 0.999. I used a second order polynomial for this one as well, and the data is okay, but it's not great. This shows that in reality, the boil temperature is a slight function of the pressure, but since you get 0.994 versus 0.999, it's 0.0005 off of perfect or experimental data, and therefore the boil temperature is a very, very weakly function of pressure. Thank you for solving this problem with me, and have a good day.